Good afternoon to all. Today I am giving a talk on X-ray diffractometry. This is Dr. A. Lakshmanda, Professor and Principal, VV Institute of Pharmaceutical Sciences, Gudlavaledu, Andhra Pradesh. Various contents in my presentation includes history, introduction, principle involved in X-ray crystallograph diffractometry, Bragg's law, and instrumentation involved in X-ray diffractometry, various applications, conclusion, and references. And first, I will give the history about the X-ray diffractometry. First of all, I will give you introduction about X-rays. X-rays were discovered by Wilhelm Conrad Röntgen, popularly called it as W.C. Röntgen, in the year 1895 while working with a cathode ray tube. This cathode ray tube is also called it as discharge tube. He observed a fluorescent glow of crystals on a table near his tube. Okay, and basing on this particular glow of crystals, okay, he unable to put a title. That's why simply he can call it as X-rays. He termed the radiation of X-rays because the nature of the radiation was not understood. That's why that rays can be called it as X-rays. And Röntgen received a Nobel Prize for physics for the because of this particular X-rays in the year 1901. And here in the year 1995, the German Post edited a stamp and dedicated to W.T. Röntgen, and they released the stamp with the name of W.C. Röntgen on his discovery. And first, I will get with the strengths of diffraction. Diffraction, in the major important strength of this X-ray diffraction is it is a non-destructive technique, and small amount of sample is going to be required in this particular technique. And it relatively the time required for this is very rapid. And by using this technique, we can identify the various compounds as well as phases. And here we can do the quantification of concentration of the spaces, and by using this particular technique we can classify various powders, but the solids are possible too. And it gives information regarding the crystallinity of the size or strain or crystalline size and orientation. And next, what are the various limitations? Every analytical technique is having their own limitations. And the first and foremost important limitation of this particular technique is basically it is a bulk technique. Unless a camera is used, we can't work this particular technique. And one more important limitation is it is not a standalone technique, often need chemical data. And here it is a complicated spectra, and we can analyze multiple phase materials, and identification and quantification can be difficult in this particular technique. Next, come to introduction about exodiffractometry. About 95% of all solid materials can be described as crystalline. When X-rays interact with the crystalline substance, this crystalline substance can also be called as a phase. And what happens in this case is once it gets a diffraction pattern. Next, what are the various X-ray techniques? X-ray techniques are popularly categorized into three different categories. One is X-ray absorption methods, second one is X-ray diffraction methods, and third one is X-ray fluorescent methods. And first, I will give you an introduction about X-ray absorption methods. A beam of X-rays is allowed to pass through the sample, and the attenuation or fraction of X-ray photons absorbed is considered to be a measure of the concentration of absorbing substance. Actually, these methods are mainly helpful in the cases, especially like elemental analysis and thickness measurements. We are using the X-ray absorption technique. Next, second technique is X-ray diffraction method. This X-ray diffraction method is one of the widely and popularly used method. These methods are majorly based on the scattering of X-rays by crystals. These methods can identify the crystal structures of various solid compounds. These methods are extremely important as compared with X-ray absorption and X-ray fluorescent methods. Totally here three different types are there. The first one is X-ray absorption method, second one is X-ray diffraction method, third one is X-ray fluorescent method. Next, the third one is X-ray fluorescent method. The X-ray fluorescent in these methods, X-rays are generated within the sample and by measuring the wavelength and intensity of the generated X-rays. Generally, these methods are non-destructive and requires very little sample preparation before the analysis can be carried out. That's why it is having the one more advantages. So, these methods are quite useful for both qualitative purpose as well as quantitative purpose too. And then come to our topic that is called it as X-ray diffraction methods. Here, what are these particular X-ray diffraction methods? These X-ray diffraction methods are majorly comes under the we can define these X-ray diffraction methods because here come to this particular X-ray diffraction method. We will get introduction. Yeah. What is a crystal? A crystal can be defined as a regular polyhedral form that can be bounded by smooth surfaces. And here, one more important aspect is every crystalline is having unique in nature. The geometric shape of the crystals reflect and internal geometry of the atoms can be explained. Next, here around all the organic compounds, 20% of the organic compounds are exhibiting the polymorphism. So, for example, if you can take the drugs like barbiturates, these groups are polymorphic in nature and several are exhibiting more than two forms also. The polymorphism majorly lies in the fact that the differences in physicochemical properties between the forms may influence manufacturing process, dissolution rate, and bioavailability. Mainly, it is focusing on three important aspects of the pharmaceutical formulations, which include the manufacturing process and dissolution rate and bioavailability. Next, come to origin of X-rays. Here, the X-ray region of the electromagnetic spectrum consisting of wavelength in the range of zero point 0.1 to 100 angstroms. Okay. Here, the most useful proportion of X-ray region for chemical analysis lies between 0.7 to 2 angstroms. Electromagnetic radiation with short wavelength and wavelength less than are considered as ultraviolet in nature. Next, here come to these particular X-rays. Here, the X-rays are generated when high velocity electrons are it is a high velocity, it is impinging on one metal target. By using this radioactive source, whose decay process results in X-ray emission, by exposure of a substance to a primary beam of X-rays in order to generate a secondary beam of fluorescent X-rays. Next, what is the diffraction? Generally, the X-ray diffraction has recently become an increasingly important technique for qualitative and quantitative analysis. X-ray diffraction gives a complete analysis of molecular structure and determination of electron distribution in the molecule. X-ray diffraction methods are generally used for mainly investigating the internal structure of the various molecules. So, okay, what is a crystal? Here in the X-ray diffractometer, the major focus is goes to crystal. Okay, and X-ray crystal may be regarded as a three-dimensional natural grating in which the atoms or molecules are arranged in a defined geometrical shape with flat faces and shaded edges. Diffraction is a scattering phenomenon. And what is and one more what the another meaning of this diffraction is it is a bending or breaking up into its component parts of a ray of light. The X-ray photons are scattered by all the atoms in the crystals. What is the major principle involved in the X-ray crystal radiation? Here, when a beam of X-ray radiation, it is a beam of X-ray radiation, it is impinging upon a substance. Then electrons are constituting the atoms of the substance. It will become a small oscillations. These are oscillating as the same frequency as that of incident X radiation that will emit electromagnetic radiation in all directions at the same frequency as the incident radiation. The conditions for diffraction are governed by mainly by the Bragg's law, and the diffracted beams are often referred as reflections. And here, the constructive interference of the reflected beams emerging from two different planes will take place if the difference in the path length of the two rays is equal to the whole number of the wavelengths. Then I will tell you the principle. The principle of X-ray diffractometry can be explained by using the Bragg's law. When Bragg and his father W. H. Bragg in 1913 employed X-rays for the first time for the purpose of studying the internal structure of the various crystals. This law gives a useful relationship between the wavelength of X-rays and the spacing between the lattice planes. It is the diffraction phenomenon. Here, when the light is impinging on these are the three different planes: plane one, plane two, plane three. When this is a light that is impinging on this particular surface, then it undergoes the diffraction like this, and the angle between this is theta. And then come to second one and reflected, third one and undergo A, B, C, like that undergo diffraction between the. Here, the distance between these two planes can be called it as a d, and the angle can be considered as a theta. Basing on this particular thing, what is the Bragg's law is n lambda is equal to 2d sine theta. 2D sine theta. Next, here this can be explained when a beam of X-rays is allowed to fall on a one particular crystal surface at an angle theta. Each atom they act as a source of scattered radiation of the same wavelength. Thus, when an X-ray beam strikes a crystal surface at an angle theta, a portion is scattered by the layer of atoms at the surface, and the unscattered portion of the beam penetrates to the second layer of atoms, where again a fraction is scattered, and the remaining passes onto the third layer. Then, basing on this, suppose you just consider a beam of monochromatic X-rays, which strikes on a set of parallel or equidistant plane in the crystal structure at an angle theta. The scattering occurs as a result of interaction of radiation with atoms located at different locations like O, P, and R. The distance AP plus PC is equal to suppose n lambda, where n is an integer that is 1, 2, 3, then that can be known as order of reflection. Basing on this, the scattered radiation will be in phase OCD and the crystal appear to reflect the X radiation. But for the diagram, AP is equal to PC and PC can be considered as a d sin theta and AP plus PC is considered as a L lambda. Basing on that, AP is 1 and say d sin theta and PC is equal to another d sin theta. By combination of two things, d sin theta plus d sin theta is equal to n lambda, finally considered as a n lambda is equal to 2d sin theta. And this equation can be considered as a Bragg's law. Then come to introduction. It is the block diagram of the X-ray diffractometer. Various components that is present in the Bragg's law instrumentation includes it is X-ray tube and the slit, collimator, monochromator, crystal, and detector, amplifier, and recorder. First here it is considered as a X-ray tube. Here it is a small slit, there is a gap, hole is there. Here you can put the collimator and monochromatic that will helpful pass to the sample. It is here you can put the crystal in this location. Then it is helpful to detect and followed by amplification and recorder. The X-ray diffraction analysis is carried out by using the instrument that is called as X-ray diffractometer. How to produce X-rays? X-rays are electromagnetic waves similar in character of light, but for the much shorter wavelength generated when a beam of high velocity electrons from a heated filament impinge on a small metal target in a sealed diffraction tube. Okay, and here what is this quality tube? It is considered as a quality tube. Okay, and here it includes the metal target. It can be acting as a anode on a tungsten filament. It will be acting as a cathode, and here it is the location of X-rays. Along with that, various components which includes the water outlet and cooling water and focusing cup and voltage circuit. The most common source of production of the X-rays is quality tube. The widely used one is the quality tube. It contains a hot cathode and a massive water-cooled anode in a evacuated glass or metal housing. The electrons are produced from a hot cathode, which are accelerated by a potential of 60 to 100 kilovolts. These electrons are strikes the anode and produce the X-rays. In this process, the cooling of X-ray tubes is most essential because only less than 1% of the electric power is converted into radiant power. Then only it can be degraded into the heat. What are the major advantages? It permits the production of X-rays of intensity much greater than that of obtainable from the stationary target. What is the major disadvantage? There is a lack of focusing of the electrons so that the whole surface becomes a source of X-rays. And another important aspect is the collimator. It is used to get a narrow beam of X-rays from the X-ray tube. And collimators are made of series of closely spaced parallel metal plates or a very narrow bundle of the tubes. Generally, the collimator is placed between the source and the analyzer crystal. And what is monochromator? And here, in order to do monochromatization of X-rays, two types of monochromators are used. One is called it as a filter chromator. Next one is crystal monochromator. Then come to filter monochromator. The X-ray beam may be partly monochromatized by the insertion of a suitable filter. And a filter is a window of material that absorbs undesirable radiation but allows the radiation of required wavelength to pass. And generally, it is used to get a monochromatic beam of desired wavelength of X-rays to fall on the sample. And what is the crystal monochromator? Crystal monochromator means a crystal means it is acting also considered as a grating. It is a monochromator made up of the crystalline materials like sodium chloride, lithium fluoride, quartz, and etc. And it is positioned in the X-ray beam so that what happens is the angle of reflecting the plane sacrifices the Bragg's equation for the required wavelength. What are the important detectors? The X-ray intensities can be measured and recorded by using the various detectors. Next, photographic methods. In order to record the position and intensity of X-ray beam, a plain or crystal cylindrical film is used. This method is time-consuming and less exposure of several hours. And here, there are different counter methods are available. One is Jigger-Muller tube counter, proportional counter, scintillation counter. And three conductor methods includes solid-state semiconductor detector and semiconductor detector. And X-ray diffraction methods. X-ray diffraction methods are generally used for investigating the internal structures. Various methods includes view photographic method, Bragg excess spectrophotometer method, rotating crystal method, and powder method. And the X-ray diffraction unit consisting of X-ray generator and goniometer. This is what is goniometer is it is an optical instrument for measuring the crystal angles. And another important aspect is the sample holder. Here you can place the sample in this location. And finally, detector can be achieved by using the X-ray detector. Then it is one of the actual live model of the X-ray diffractometer, okay, which includes counter, X-ray source. It is a crystal where you can locate in this place in this particular location. Anti-scatter slide and collimating slide and nickel filters can be used, and finally jiggle tube can be placed in this location. That is one of the appearance of the X-ray diffractometer. And nowadays, so many automated X-ray diffractometers are also available. With the development of electronic X-ray detectors and mini computers, X-ray diffraction has become automated so that the time and effort of determining the structure of the molecule has been substantially reduced. And after computer analysis of the data, directly we will get the molecular structure of the crystal can be obtained. Okay, and next, what are the important applications? Here, the important applications of this particular X-ray crystallography diffractometry is structure of crystals. Here, by using this particular X-ray diffractometry, what happens in this case is the structure of the crystal can be determined. And second important aspect of this application of X-ray diffractometry is we can then the characterization of the polymers, especially in the pharmaceutical formulations. So many polymers we are using, and the characterization of polymers is also plays important role in the polymer science. That's why that characterization can be achieved by using this X-ray diffractometry. And third and important aspect in this case is particle size. Here the X-ray diffractometry can also be used for determination of the particle size also. And the next other important application is, in the inorganic chemistry, it is having the good application. What is that one is? One is study of metals, and next one is study of non-metals, and study of inorganic compounds, and study of interstitial compounds, and like that. All these are various applications in the inorganic chemistry. In a similar fashion, the X-ray diffractometry is also having the applications in the organic chemistry also. On how the X-ray diffractometry is useful in the organic chemistry. It is useful for identification of dibasic acids. And another thing in this case is identification of the various carbonyl compounds like aldehydes as well as ketones. Another thing is identification of the amines. Next, structure of proteins. Next, determination of the absolute concentrations. Okay, and all these things can be achieved by using the X-ray diffractometry. Next, study of pharmaceutical compounds. Here, the study of polymeric forms of the drugs, like the drugs includes carbamazepine and ranitidine. Okay, and here, of course, we know very well what is the polymorphism, the phenomenon of mixing up of different orbitals to form the same number of identical orbitals of an atom. Okay, it can be considered as a polymorph, and the phenomenon is known as a polymorphism. And here, this carbamazepine and ranitidine is exhibiting this one. Next, characterization of the drugs. And here, what type of the drugs can be characterized by using this one? For the first and foremost importance is cyclophosphamide. Okay, and next another important goes to structure of the drugs. Here, especially by using the X-ray diffractometry, we can determine the structure also with these examples of this particular structure, which includes penicillin and vitamin B12 also. Another important aspect is structure of alkaloids and steroids. Okay, and here the alkaloids and steroids are having the very little complicated structures. These complicated structures can be identified by using the technique that is considered as a X-ray diffractometry. Next, along with that, it is also having the various other type of the applications, which includes determination of the cis-trans isomerism. Okay, and this cis isomerism, trans isomerism, both can be identified by using the X-ray diffractometry. Next, determination of the linkage isomerism. How, what type of linkage that is there between the isomers, that can be achieved by using this particular X-ray diffractometry. Next, structure of alloys. Okay, that can be done by using X-ray diffractometry. Structure of isomorphous compounds. Okay, and study of the coordination compounds, and study of the hydrogen bonding, a study of corrosion products, and analysis of detergents. Along with that, these X-ray diffractometry can also having the application in the quality control also. Okay, and one of the simple point in this case is mainly it is used to screen the materials for the impurities in quality control, and to identify the phases in the material, and to assess the natural and synthetic minerals, and detection and measurement of the trace elements in fertilizers. Okay, like that, it is having the wide applications in various divisions, which includes inorganic chemistry and organic chemistry, and also in the agriculture and fertilizers in all the areas. It is having this one. And finally, we can conclude the topic of X-ray diffractometry. Already here, the X-ray diffraction is considered as an indispensable tool for the present day analyst and chemist and biologist. With the major transformations undergoing in pharmaceutical industry and a dramatic increase in number of new chemical entities, the XRD has become one of the important tools for characterization of the pharmaceutical solids. Okay, and mainly at this junction, we can say that the XRD, that is X-ray diffractometry, is widely used for characterization of the pharmaceutical solids. And here at this particular topic, what we can say is we can cover various important components about the XRD. The first you can started with the introduction about the X-rays, and followed by what are the various techniques that are involved in X-ray scattering methods. Okay, like diffraction, that is fluorescence, and X-ray reflection, everything that is covered on that one, and followed by then our topic is majorly focused on the X-ray diffractometry. That way, the major thing is which instrument that is used. The instrument that are used in this technique is the X-ray diffractometer. The X-ray diffractometer, what is instrumentation involved in the X-ray diffractometer, and what is the principle involved? Here, the major principle involved in the X-ray diffractometry is considered as a Bragg's law. Bragg's law. What is Bragg's law? Bragg's law is considered as a n lambda is equal to 2d sine theta. That is one of the important technique. That is the principle, and followed by next. What type of counters that are used. Okay, Jaeger counters and etc. Okay, another thing is how to analyze the samples, what type of detectors that are used, what is the quality tube, what is the collimator, everything that is explained in this particular presentation. And after that, the first and foremost important aspect in the X-ray diffractometry is why we are using this X-ray diffractometry. Okay, and here this X-ray diffractometry is majorly used having the wide applications in different areas, which includes it is used in organic chemistry, it is used in organic chemistry, it is used in agriculture science, it is used in fertilizers. Like that is having n number of examples that are used in this particular cases. Okay, and finally we can conclude this topic with the references. Here we have covered we got the information of various very standard and international books. The first one is Handbook of Instrumental Technique for Analytical Chemistry by Frank and Sutil, and Chemical Structure Analysis by A. Primer, and The Basics of Crystallography by C. Hammond, and X-ray Analysis and the Structure of Organic Molecules by J.D. Dunitz, and Instrumental Methods of Chemical Analysis by Willard, and the Principles of Instrumental Methods of Analysis by Skoog, and Instrumental Methods of Chemical Analysis by G. Chatwal, Instrumental Methods of Chemical Analysis by B.K. Sharma, and Practical Pharmaceutical Chemistry Part 2 by A.H. Beckett, and Instrumental Methods of Chemical Analysis by H. Kaur, Introduction to Instrumental Analysis by R.D. Brown. Okay, and dear audience, by using this particular X-ray analytical technique, we got the very good information regarding the how to analyze the samples. Especially here, our focus is mainly on the pharmaceutical solid samples only, because the X-ray crystallography is majorly useful for the study of the solid samples only. Okay, that's why especially for the solid pharmaceutical samples, this technique is widely useful. By using this particular technique, we can characterize the samples. That is the major advantage of this particular X-ray diffractometry. Okay, thank you for your patient learning. Thank you very much.